In this video, we're going to start taking a look at some calculus concepts. In particular, we are going to look at the derivative. So let's take a look at our definitions, things that we are familiar with from our calculus days. So let f be a real valued function defined on an interval I that contains the point c. We say that f is differentiable at c, or it has a derivative at c, if this limit here exists and is finite. We denote that using our standard notation f prime of c. So we can talk about the derivative at a point. Then we can extend this idea and say, what if it is differentiable? What if our function is differentiable at every point in some set S that's contained in an interval? Then we say that it's differentiable on the set. And if we look at this function f prime that maps from S to R, this is called our derivative of f on S. So those are our definitions for differentiable at a point, and then the differentiable on a set, the derivative of a function. With those, we then have some theorems that are going to be true. So let I be some interval containing a point C, and suppose that f maps from I to the real numbers. Then that function f is differentiable at C if and only if every sequence x sub n in I that converges to C with values of x sub n not being equal to C, those sequence, then the sequence f of x sub n minus f of c over x sub n minus c should converge to f prime of c. Right? So f is differentiable at c if and only if, no matter what sequence we have that's convergent to c with the values of x sub n not equal to c. If we have a sequence that converges and the sequence f of x sub n minus f of c over x sub n minus c converges to f prime of c. Let's take a look at a second thing that we know that is true. So theorem 6.1.6, it says here, if we have this function from I to R, if this function is differentiable at a point C, then it has to be continuous at that point C. Right, so if we have this function and we know we have differentiability at C, then it has to be continuous at C. So let's go through and we will take time to prove this. So to prove this, we would note that for every single value of x in I with x not equal to c, we have f of x should be exactly the same thing as x minus c times f of x minus f of c over
I don't know that.
x minus c plus f of c. So notice here this f of c would cancel out with this f of c, or x minus c cancels with this x minus c, so then the negative f of c and this positive f of c would cancel out, and so we just get f of x. Right? So those two sides are equal. And so now we can then make the observation since f prime, the derivative at c exists, since the derivative at c exists, we know that the limit of f of x minus f of c over x minus c is equal to some value, call it f prime of c. This is some value in the real numbers. Okay, so what? So what does that tell us? Thus, we know that the limit of f of x as x approaches c should be, so this is up here, should be exactly the same as the limit of x minus c f of x minus f of c over x minus c plus f of c as x approaches c. This limit, this part here, the x minus c, that should be approaching 0. This stuff here is approaching f prime of c, which is a real number. And this is just a constant, so that is just f of c. And so we get the limit of f of x as x approaches c is equal to the value f of c. Thus, or therefore, f is continuous at c. Beautiful. In the next video, we'll take a look at some of our derivative rules. We'll see you then.